So next we'll be looking at a practical example where we have a function. So let f of x represent the loudness. So this is measured in decibels. So the symbol for decibel is dB, of a jet engine at a distance of x meters away. So if you're x meters away from the engine, f of x will tell you how loud the engine would be at that distance. So it's a measure of the loudness in decibels. So we want to interpret the following expressions practically. So the first one is f of 50 is equal to 140. The second one, f inverse of 80 is equal to 50,000. The third one is f prime of 50 is equal to negative 0.1737. The fourth one is f prime inverse of negative 0.1086 is equal to 80. And then the fifth one is f inverse prime of 140 is equal to negative 5.7565. So we have these statements. These might be some things that you see, equations that you see somewhere, and say, well, if f of x is the loudness of a jet engine at a distance x meters, what would it mean if somebody tells you that f prime inverse of negative 0.1086 is equal to 80? What does that mean practically? In other words, if you were to go on a TV show and explain this without using calculus, how would you explain it to somebody who had no math knowledge? So that's the key goal here, is to explain each of these expressions to somebody without using any mathematical notation or terminology. And so the first thing is to assign a variable name for the output. So we have the loudness, so let's go with, how about L? Sound good? So we'll say L is equal to f of x. So the loudness at distance x is related by this way, which means that x is equal to f inverse of L. So that's the function f and its inverse function. You see, now that we have a variable for the output, we can write this in notation. X is equal to f inverse of L. Now, with this, we can already look at number 1 and number 2. So for number 1, what does that mean practically? F of 50 is equal to 140. Well, 50 has the place of x, and 140 has the place of L. And number 1's the easiest because they tell us what the function f represents, what the function f means practically. F of x is the loudness in decibels of a jet engine at a distance x meters from the engine. So number 1, x is 50, and L is 140. So number 1 says, at a distance of 50 meters, the loudness of the engine is 140 decibels. Or if you're 50 meters away, the loudness of the engine will be 140 decibels. For the second one, the roles are reversed. So L is now the input of f inverse and x is the output. So the input is L and the output is x. So for number 2, I can just make a note on the side. For number 2, the input is L, so L is equal to 180, and the output is x. So the correspondence is 80 and 50,000. However, for number 2, it's saying f inverse of 80 says, well, how far do you have to be for the loudness to be 80 decibels? And the answer is 50,000 meters away. So we can say the distance at which the loudness is 80 decibels will be 50,000 meters. Remember, so once you get the idea, you can kind of rephrase and say, okay, was this really how I would say it? The distance at which the loudness is 80 decibels will be 50,000 meters. You can say, in order for the engine to be only 80 decibels loud, you have to be standing 50,000 meters away. I think that's probably the best way to approach it. I'm a little bit skeptical that that's actually how far that you have to be, but we'll take it for what it is for the moment. But I wonder if that seems like a huge distance. It's surprising. 50 kilometers, that cannot be right. But anyway, let's just take it for what it is. If this is the statement that was given to you, it means that you have to be standing 50 kilometers away before the loudness is just equal to 80 decibels. So the first two we can check off. Now the next ones are the ones that get a little bit more complicated. The next one's not too bad, it's just the derivative, and the final two are the complicated ones. So taking the derivative of the function f, we get dl dx is equal to f prime of x. And then taking the derivative of the inverse function, we get dx dl is equal to f inverse prime of L. Right. And then the final segment will be the inverse of this one. So the inverse of this, we would get x is equal to f prime inverse of dl dx. So right away for number 3, 4, and 5, we can see what all those numbers represent in terms of the symbols. So for number 3, 50 is x, and negative 0.1737 is dl dx. So for number 3, what we can say, actually let me just clear off some space at the bottom instead of starting a new page. So for number 3, we would say that at a distance of 50 meters away, so at a distance of 50 meters, so this is the rate of change, it's dl dx. So this tells me how much the loudness will change if I increase my distance by an additional meter. So it means if I stand approximately 1 meter further away, so for every change in x, I should expect approximately this much change in the loudness. So at a distance of 50 meters away, the loudness will decrease so it's a negative, which means that it's going to decrease by approximately 0.1737 decibels if you were to stand 1 additional meter farther away. So if you're standing at a distance of 50 meters from the engine, number 3, f prime of 50 is equal to negative 0.1737. What that means is that if you're at 50 meters from the engine and you decide to stand 1 meter farther away, that the loudness will decrease by approximately 0.1737 decibels. Now you don't want to say for every meter farther away that you stand that it will decrease by this, because this is just a local approximation. And in fact, the smaller the step, the more accurate this gets. So if you stand 1/10 of a meter farther away, the loudness will decrease by approximately 1/10 of this, right? So that's going to be even a better approximation. But basically the whole meaning of this is that when you're 50 meters away, this is the change in the loudness if you increase your distance by 1 additional meter. So if you move 1 meter farther away, the loudness will decrease by approximately 0.1737 decibels. So the last two are probably the most tricky. So number 4, let's see. Yeah, I guess let's do number 4. So number 4 is basically the derivative and then the inverse function. So it's basically exactly the same as number 3, except the outputs are here and the inputs are here. And except we want to state it a little bit differently. So basically for number 4, x corresponds to 80. So if we're looking down here, the output would be x, so the output is 80. And the input is dl dx, so the input is this thing right here. So this is dl dx, and that's x. So that's x, and this is dl dx. So, but since dl dx is on the inside, let's start with that. So we say, when this is true, then you must be 80 meters away. So we'll just say basically the same thing, except structure the sentence a little bit different. So, so we'll say at the point. So if you are standing at a point, if you are standing at a point such that if you increase your distance by 1 meter, the loudness will decrease by approximately 0.1086 decibels, then you are 80 meters away. So basically we can say that the point at which an increase of 1 meter in distance results in a decrease, so that's negative, that's the negative sign right here, decrease of approximately 0.1086 decibels, then the distance is approximately 80 meters away. So it literally corresponds to, at a distance of 80 meters, you'll have a decrease of 0.1086 in the loudness, 0.1086 decibels in the loudness for standing 1 meter farther away. So we'll start with the 0.1086 because that's the input. And then finally, for the last one, so number 5, so we got 3 and 4. So 3 and 4 are basically the derivative and its inverse function. Number 5 is the last, is maybe the most tricky. It's the derivative of the inverse function, so you have to think about this a little bit differently. So first you have to look at the relationship for the inverse function. X is on the outside, L is on the inside. So when you take the derivative of that, it's a derivative with respect to L. So L is still on the inside, and now the outside is dx dl. So this one here corresponds to a dx dl, and then the inside corresponds to an L. So we can say when the loudness is 140 decibels, so this is dx dl. So it's how much the distance has to change so that the loudness changes by 1 decibel. So when or at the point in which, maybe when is not good because it implies time. So if you're standing, or say at the point in which the loudness is 140 decibels, if you decrease your distance or let's say if you, let's get even more practical. So if you instead were to stand approximately 5.7565 meters closer, the loudness would increase by 1 decibel. Right? So basically, at the point in which the loudness is 140 decibels, in order to affect a 1 decibel change in your loudness, you'd have to, so in order to increase the loudness by 1 decibel, you would have to stand approximately 5.7565 meters closer. So that's how you would, unpackage this one right here. So that's basically, make sure that you get always the units right and describe these things. But once you have this map over here, you can basically just see, oh, I see what's happening. It's a dx dl. So this is for for a single change in decibel. If you want to be 1 decibel louder, this is how much I would have to change my distance approximately to get that result.